Have you ever wondered how our solar system with its diverse planets came into existence? The universe is brimming with enigmas that have intrigued the human mind for millennia. Among these mysteries, one question that has particularly piqued our curiosity is, how did our solar system form? How did this vast expanse of space, filled with a fiery sun, rocky planets, gas giants, and countless asteroids and comets, come into being? Enter the nebular hypothesis, a scientific explanation that seeks to shed light on these very questions. It's a theory that takes us back billions of years, to a time when our solar system was nothing more than a cloud of gas and dust. The nebular hypothesis provides a fascinating narrative of cosmic evolution, tracing the journey from a swirling nebula to the formation of our unique solar system. Let's dive into the nebular hypothesis, an explanation as old as the stars themselves. The nebular hypothesis, first proposed in the 18th century, offers an explanation of our solar system's formation. A revolutionary idea, it paints a picture of our cosmic neighborhood's humble beginnings and brings us closer to understanding the origins of our very existence. So, what exactly is the nebular hypothesis? Imagine, if you will, a vast, swirling cloud of gas and dust. This is the solar nebula. It's not just a feature of our solar system's origin story, but a common starting point for countless planetary systems across the universe. This nebula, rich in elements like hydrogen and helium, is the birthplace of stars and planets. And it's from this chaotic primordial soup that our solar system emerges. According to the nebular hypothesis, our solar system began its life as a part of this immense rotating cloud. Over a span of millions of years, gravity, the great cosmic sculptor, began to pull this nebulous material together. With time, the cloud started to collapse under its own weight, spinning faster and faster, flattening into a pancake-like shape, a protoplanetary disk. At the heart of this disk, where the pressure and temperature were highest, a young sun began to form. Around it, the remaining dust and gas continued to orbit, gradually accreting into planetesimals and eventually the planets we know today. The nebular hypothesis, while an elegant and widely accepted theory, is not without its challenges. There are questions it doesn't fully answer and phenomena it doesn't entirely explain, but it remains an essential part of our understanding of planetary formation. It is a testament to the power of scientific inquiry and the enduring human curiosity about our place in the cosmos. But how did this nebula transform into the organized system we see today? As we delve deeper, we'll explore how the chaos of the nebula gave birth to the beautiful order of our solar system. So, buckle up, as we embark on a journey through time and space, to the very beginnings of our celestial neighborhood. The first step in this cosmic transformation was the formation of the protoplanetary disk. Picture a dense cloud of gas and dust known as a solar nebula. It's an unassuming entity, quietly existing in the vastness of space. Yet, within this nebula, a remarkable transformation is about to unfold. Its destiny is set in motion by a slight disturbance, perhaps a passing star or the shockwave from a distant supernova. This disturbance triggers a gravitational collapse, causing the nebula to contract. As the nebula shrinks, the law of conservation of angular momentum ensures it doesn't collapse into a single point. Instead, it starts to spin faster and faster, much like a figure skater pulling in their arms during a spin. This rapid rotation causes the nebula to flatten into a spinning pancake-like structure. This is the birth of the protoplanetary disk. This disk is a bustling hub of activity. It's composed mostly of hydrogen and helium, with sprinklings of dust and heavier elements. The core of the nebula, now a hot, dense region known as the protostar, sits at the very center. Around it, the rest of the material in the disk orbits, kept in check by the protostar's gravity. This material isn't just idly spinning around though. Oh no, it's hard at work. The dust particles within the disk start to collide and stick together, forming larger and larger clumps. These clumps eventually grow into planetesimals, the building blocks of planets. Meanwhile, the protostar in the center continues to contract, growing hotter and denser until it ignites nuclear fusion, marking its transition into a full-fledged star. The protoplanetary disk is more than just a cosmic spinning top. It's a celestial factory, churning out planetesimals and paving the way for the birth of planets. It's the stage where the raw materials of a nebula are transformed into a functioning solar system. This disk wasn't just spinning in space, it was the birthplace of our planets. Within this swirling protoplanetary disk, the seeds of planets began to grow. Picture a cosmic dance where dust and gas, drawn together by the force of gravity, begin to coalesce into larger and larger clumps. This is the process of planetesimal formation. The first step in the birth of a planet. The protoplanetary disk is a bustling nursery of these planetesimals, each one a potential planet in the making. As they whirl around the young star at the center, they collide and merge, growing larger as they gather more material. These are no gentle mergers. Imagine massive collisions at mind-boggling speeds, with the resulting heat and pressure fusing the colliding bodies into a single, larger entity. As they grow, these planetesimals evolve into protoplanets, objects large enough to exert a significant gravitational pull, but not quite large enough to be considered a full-fledged planet. They continue to sweep up material from the disk, growing larger and larger. Their gravitational pull increases, allowing them to attract even more material and grow even faster, a process known as runaway growth. But here's the fascinating part. Not all of the protoplanets make it to planet status. Some collide with each other in massive impacts, sometimes resulting in the formation of moons. Others are flung out of the system entirely by gravitational interactions. It's a cosmic survival of the fittest, with only the most robust protoplanets making it to the final stage, becoming a planet. Eventually, after millions of years, the dust and gas in the protoplanetary disk are mostly depleted, either incorporated into the planets or blown away by the young star's radiation. What's left are the planets, each one a testament to the tumultuous and violent process that birthed them. And just like that, from a cloud of dust and gas, the planets of our solar system were born. The process may be chaotic and violent, but the result is the harmonious dance of planets around their star, a dance that has been ongoing for billions of years, and will continue for billions more. The nebular hypothesis, then, gives us a compelling timeline of our solar system's birth. Let's recap the journey we've embarked on through the nebular hypothesis. This theory paints a vivid picture of our solar system's emergence, starting from a cloud of interstellar gas and dust, known as the solar nebula. This nebula, composed primarily of hydrogen and helium, along with traces of heavier elements, set the stage for the birth of our cosmic neighborhood. Gravity played the leading role, causing the nebula to collapse under its own weight. As the nebula shrunk, it spun faster and faster, flattening into a spinning disk of gas and dust. This was the protoplanetary disk, the stage where the real magic happened. The heart of the disk, under immense pressure and temperature, ignited to form the sun. Farther out, dust particles began their intricate dance, sticking together to form larger and larger clumps. These clumps, or planetesimals, were the building blocks of planets. In the inner regions of the disk, rocky and metallic planetesimals came together to form the terrestrial planets. Farther out, icy planetesimals accreted, forming the cores of the giant gas planets. Over millions of years, these embryonic planets swept up more and more material, growing in size and mass. The planet's gravity cleared their orbits, creating the ordered system we see today. Even the leftover debris played a part, forming the asteroid belt, comets, and the distant Kuiper belt. But remember, the nebular hypothesis isn't a closed book. It's a living theory, changing and evolving as we gather more data and refine our understanding of the universe. It's a testament to our human curiosity and our desire to unravel the mysteries of our cosmic origins. And while there's still much to learn, the nebular hypothesis provides a fascinating glimpse into the origins of our cosmic neighborhood.